All right. So I'm going to go ahead and get started. We're like 1 minute early or whatever, but I think that'll be all right. So welcome to Bridge Engineering. I hope you all have fun this semester. I think I will, at the very least. This is one of my really favorite classes to teach. I mean, bridge engineering is really what I claim to do. Like a bridge engineer, that's really who I am. So I always sort of jump at the chance to teach this class, and hopefully you all will have a lot of fun with it. Let's get some housekeeping stuff out of the way. So I'm going to pass the syllabus out. So let's see. Everybody sit in one big line. That makes this somewhat easy. So I'll give you that, and then that, and whoa. I was never good at table hockey. All right. I have a separate syllabus for you all, and we will talk about this later on. So, like I said, for senior design folks, I'm going to have you all stick around a little bit after class. So, all right, there you go. Okay, so I've got here some notes that kind of cover just some general stuff in regards to this class. So let's see. All right. So let's talk a little bit about the grading, because since I'm sure you all are interested in that. This class, more than any, is really heavily dependent on your homework and the design project that we do later on in the semester. So a lot of the grade is really emphasized in that. There's going to be a research presentation that you all are going to do. I'm going to mention that here in a little bit, but that's just going to be included in the homework. We're just going to take a week, and you all are going to each do like a little 10-minute presentation or whatever on a given bridge failure, but we'll talk about that here in a little bit. I'm sure you all are interested about textbook. There is none. To be honest, I've done my best to try and search for a good textbook on this topic that's cost effective, and there really isn't one. But one of the nice things about bridge engineering is that there's a lot of available resources online. A lot of different industries, like the steel industry and the concrete industry, they like to sell more bridges, so they put a lot of technical information online in the hopes of making it easier on engineers to design them. So there's a lot of stuff available online. Now, in terms of the specifications, we're going to be designing, or at least our lecture and our methods are going to be going off of the AASHTO LRFD spec. I'm going to be giving you all pieces of the LRFD spec throughout the semester. If you've ever seen a copy of the AASHTO LRFD bridge spec, it fits in a 3-ring binder, and it's about yay thick. So I'm not going to give you all of it. That would kill a lot of trees. But I'm going to give you the pieces that you need. Now, I guess technically I'm supposed to get them back at the end of the semester, but we'll talk about that near the end. It's not really the biggest deal in the world. One other thing I'll mention, the bridge industry is very, it's really difficult sometimes to keep up with the latest edition of the spec. I mean, it wouldn't surprise me if by the time the semester's over, there's already a new edition. There's always new additions, new revisions, interim revisions, and whatnot. I'm going off of the 7th edition for a few reasons. The 7th edition was released in 2014, so it's not exactly like it's old. It's a relatively recent spec. But there's some software packages that we're going to use later on in the semester that are built directly off of the 7th edition, so I wanted to make sure everything matched. But for the purposes of what we do in this class, a lot of this stuff hasn't changed for a long time and arguably isn't going to change for a while. So it's not really going to affect us. Most of what we do in here is going to be focused on steel bridge design, and that hasn't changed, or the spec hasn't changed in that regard since like 2004. So it doesn't really matter. All right. Any questions so far? Okay. So let's talk a little bit about the homework. This class and this science, this topic of bridge engineering, is a topic that lends itself very heavily to Excel. You're going to be doing a lot of calcs sort of over and over again when you iterate your designs, and Excel is a really really user-friendly means of doing bridge design. So most of the homeworks that you have this semester are going to be things like I give you an assignment and you prepare an Excel sheet to do some type of calculation, to do, you know, section property calcs or liability distribution factors or whatever. And you'll just turn that in, and that'll be your homework. So if you aren't familiar with Excel, I'd say get familiar with Excel because you're going to use quite a bit of it, okay? But there's plenty of stuff available for you to get refreshed. My big thing, just make sure that your homework is neatly formatted. Just don't give me an Excel sheet where there's stuff all over the place and it's a mess. The big, sort of rule of thumb, if I can print this out and it's easy to follow, then it's good to go. All right, so far so good? All right. Let's talk a little bit about these research projects. So I don't really want them to be, they're not going to be that big of a deal, like in terms of, it's not going to be like this massive part of your grade, but I want you all to do, or to at least get familiar with a little bit of independent study on your own. So what I'm going to do is this. I'm going to sort of at random assign all of the bridge engineering students in this room a bridge that failed, okay? And what you're going to do is come in and give, about a 10-minute presentation or so, something like that, telling us why it failed, what happened, how did it affect the industry? Was there something that we learned from this this failure that affected designs to come? Something like I think of something like the Yellow Mill Pond Bridge, which you all might not have heard of, but that was a failure that happened sort of back in the day, and it greatly affected how we do fatigue assessment according to the spec. So stuff like that, and just a short 10-minute presentation. I just want to make sure it's well researched and that you know what you're talking about, but no big deal. And I've sort of tentatively scheduled that we'll do those presentations on November 15th, which is when we're all done, we'll bounce for Thanksgiving and what have you. Sound good? All right, we've got two that comes later. Let's talk about the design project. All right, so design project. The design project that we're going to do in this class is a simply supported composite steel plate girder bridge. And most of what we do in this class, I say most, but it's really our main focus in this class is going to be on steel bridges. And it's not because I'm partial to steel bridges, but it's because if you're interested in concrete bridges, we have an entire course devoted to that. We have pre-stressed concrete. So there's really no point in doing that again. Pre-stressed concrete is all about the concrete aspects of that type of design. There's not really a course where you learn about steel plate girder design because that course is this one. So that's really what we're going to focus on. Now the first, I'd say, maybe 3 weeks, 4 weeks, something like that, is for the most part superstructure neutral. Like the live loads on a bridge don't care whether the bridge is steel or concrete or what have you. So that type of material is going to apply to all types of bridges. But when we get to our specific types, they're going to be steel. So what I'll probably do is it's going to be a simply supported bridge. I'll do something similar with the research project. I'll come up with different span lengths and cross frame spacings and what have you, and you'll each sort of go to work and prepare the calcs for your independent girder design and come up with at least some rough drawings to illustrate what your final design is going to be, and you'll just turn that in the last week of the semester. So you'll have plenty of time to do that. Sound good? Okay. Last, exams. I have here that I was going to do exam 2 during the final lecture period. Now I'm thinking about it, I think I'm probably going to do 2 take-home exams. Just sort of like midterm or final. You all take it home, bring it back the next week. You all are grown-ups, so you all should be able to assess that. The exams, I mean, they're usually not the biggest deal in this class. I mean, if you can do the homeworks, you should be well equipped to do the exams. It's just sort of I guess the best way to put it, it's just something we got to do. So that's sort of the way I look at it. All right. Sound good? Any questions about the organization, about what it is we're doing in here? Anything at all? Okay. I just want to spend a little bit of time tonight just talking about just bridges in general and just some overviews. There's not really a great, one significant point I want to make about this stuff. There are some little points I want to make throughout, and I just want to get us thinking about bridges and get that thought process going. Now I've got some lecture notes I'm going to pass out. Let's see, I'll hold this one for now. Let's see, I think that's good there. I think that'll work. Let's see. There's that. For some reason, I kept you all separate. I don't know why. What's that? Your words, not mine. All right, there's that. Let's see. What else am I forgetting? Oh, I might as well get the sign-in sheet started. So I take attendance. I split us up into two groups because we've got some folks doing their senior design project similarly with us as well. So I'm just going to pass that around. Excuse me. Okay, so I've just got some an overview of just some general bridges and some nifty things, some older things, some newer things, just stuff I thought was kind of interesting. I can just tell you for a fact, or as far as I know, this is a fact. I don't think there are any bridges in West Virginia that are this old. Am I right on that, or? We don't build them like we used to. This is a bridge that's in service, carrying vehicular traffic. Just think about that. Those are 2,000 years old. I mean, I just think that's worth mentioning. There are some very interesting characteristics about this bridge. I mean, it's not in, I don't want to say, it's not in super fantastic shape, but it's still working. It has some features, though, that are very, I want to say, somewhat consistent with some of the bridges that we do today, though. The arch structure that they're using. I don't know that we build bridges exactly like this anymore, but some of the features, the way that the depth changes across the span, some of that stuff you still see to this day. This is just another example of one of those historic arch bridges that, again, still in service, hundreds of years old, and still doing fine. Our design life for bridges in the United States is 75 years. There's talk of extending that to 100 years in some of the next cycles of the code, but I don't think anybody's thinking this far ahead. I don't think they're there yet. This is really the kind of bridge we're going to be focusing on this semester, a continuous span plate girder. This is a pretty simple example of one in terms of its geometry. These bridges can get a little more funky, as we'll see here later on. There are a number of things about this that are worth pointing out, that if you're not in that mode of thinking about bridges, can sort of you sort of gloss over, but it's stuff that the bridge engineer really needs to consider. Like for instance, I don't know about you, but that bridge to me looks a little bit longer than 100 feet. Looks a little bit longer than that, right? Well, because of that, we cannot truck those beams to that site in one single piece. They have to come in pieces, and they have to be spliced together. Where do we locate those splices? That is actually an important point to consider, and something we will discuss throughout this semester. Okay? Now this girder has a uniform depth, or at least for the most part looks like it has a uniform depth. we can vary that, and in some cases, it's very advantageous to vary the depth in order to increase the economy. If you can shave some weight off of that section without terribly increasing the weight or terribly increasing the complexity of the fabrication, you're going to want to do so. Some other interesting things that are worth mentioning, if you go back to your structural analysis class, wherever you took that, I'll bring up something that you might have remembered. Remember when you were drawing moment diagrams, you might have heard the term, smiley face positive, frowny face negative. Remember that? That would tell you the sign convention for your moments. Well, there are instances on this beam where if we apply load to it, as it's got load right now, some of these sections, particularly the sections between those piers, are going to be bending positively. Across the piers, though, like right here or right here, they're going to want to bend negatively. And that's really important to consider because the material can behave fundamentally differently. If we talk about those negative bending regions tell me on top of that bridge is a concrete deck. That concrete deck, is it going to be in tension or compression? Right here. It's going like this. It's in tension. And concrete is a material that behaves very, very poorly in tension. So generally, if we start looking, at these plate sizes and these beams, these beam sections, we're going to find much larger plate sizes right around the piers than we are in the main span, because the concrete is ineffective in that, around that pier. So that's just, some little points I want to make, throughout this presentation. Like I said, this is going to be, generally the type of bridge that we're going to need to discuss. This kind of brings up some of the points I was mentioning earlier. You can't bring these sections all in one piece. You have to splice them together. So how you design those splices, where you locate them, is very, very critical. Also, there's not just, 4, I-beams supporting these loads. There's a series of cross frames and whatnot. Those cross frames provide the lateral stability for that structure, making sure the whole structure doesn't want to topple over during construction and what have you. So that's, and not only during construction, but if we're dealing with something like this, like this bridge on the right, this horizontally curved flyover, those cross frames become main load-carrying components of the structure because that structure is wanting to turn over just because of its geometry. It's really wanting to twist. So those cross frames prevent that, and they can see a fair amount of force. There's also, and I don't want to get too much into detail with this, but even just the detailing for elements like this can get really funky because as you apply loads to these elements, obviously they're going to want to deflect. Okay, and if you've got something like this horizontally curved flyover right there, just how you detail it such that you can actually put it together so that these cross frames will fit together during construction and that you don't generate these massive additional stresses, that can be kind of challenging and a little tricky throughout the construction process and throughout the design. So stuff like that's things you've got to consider. Another thing that's kind of interesting about this, and this is a really I guess I'd say this is a unique aspect of bridge engineering. Structural engineers tend to deal with mostly buildings and bridges. And I would argue that with bridges, what can be more critical through the design process is the concept of staged construction. What do? We take, we've got this bridge. The first thing we do, we set the beams. We connect the cross frames. Then we set our formwork. Then we pour the concrete deck. Then the concrete deck cures. That construction process happens in stages. Well, during each one of those stages, that beam, that girder, is seeing some amount of stress. What's kind of interesting is when you find bridges like this, these really funky bridges with crazy geometries and crazy skews and what have you, for bridges like that, sometimes the worst case scenario in terms of stress is actually during construction. In other words, the most unsafe region throughout the whole process is during the construction. Once the bridge is complete, it's not going anywhere, So it's kind of an interesting aspect that we have to consider. One of the things that we'll spend a fair amount of time on in this class is looking at a concept called constructability. Not, because we have to answer the question, well, yeah, the bridge is safe, to carry the truckloads and the vehicles, but can we safely even put it together? Can we safely erect it and construct it? That's an important point that we're going to need to consider. This is sort of what I was mentioning earlier, this concept of changing the depth of the section. One of the things that you kind of notice is we've got this beam, and notice how the depth changes along the span. The beam is deepest right here, right at the piers. See that? That's because if you take a look at the moment diagram, you take a look at the moment diagram, you'll find that the largest moments are right there at the pier. And we can see examples of that, around here as well. Go to Charleston, or right there near Nitro and St. Albans, and look at those massive trusses that cross the Kanawha River. Just take a look at them, and you'll notice the trusses sort of point up like that. I know some of the folks in the area, have y'all seen that? Well, why do we have that massive depth right at the pier? It's because that's where the largest moments are. Now, granted, it's a truss, and we don't think about moments when we look at trusses, but the concept is generally the same. Depth equals stiffness, and we need that deeper section where we've got those larger forces. So it's just something to consider. This is just another example. They had some significant elevations they had to meet on either end of that construction project. So that's really all I have to say about that, other than those are some really tall piers. I don't know, I just thought that was nifty. Now, while we are primarily in this class going to be dealing with I-beams, top flange, web, bottom flange, that's not the only option when you're looking at steel. There's also the concept of box girders. A box girder, you only have a single bottom flange, but you have two webs and two top flanges. They can be pretty advantageous when you've got bridges, they can be advantageous when you're looking at something like this, when you've got crazy curves and skews and what have you. Box sections tend to have better performance under twisting, under torsion, and because of that, that's why they're so advantageous in curved bridges. You tend to see them used quite a bit in those instances. You do see them here and there on straight bridges. I'd argue not as much, although there's a number of these actually in the Charleston area as well. You can see a lot of box girder bridges there where the 64 and 77 and 79, where all those sort of cross over. You can see a fair amount of box girder bridges there as well. The construction's fairly similar. I think it's kind of nifty to note that just like I-beams, you need cross frames for box girders, but unlike I-beams, they're inside, or for the most part, they're inside. I mean, you can have them on the outside as well, but usually we place cross frames on the inside of the box girder. And this is just the erection. Again, same questions we've got to answer. They come in pieces, and we're going to have to splice them together. Where do we place that splice so that we have an efficient construction process? And sometimes there is no simple answer. I mean, you've got to consider shipping considerations, material availability. Stuff like this are questions that civil engineers need to answer. And sometimes there's no great answer. There's a bunch of bad answers, and it's the least bad. So sometimes it is what it is. It's just real life. I throw this in here just to show some other options. We have a few of these in the West Virginia area, but we can erect what I would call rigid frame bridges, where the portions of the substructure and the superstructure kind of meld together. Some other interesting aspects of that, I tend to think this is a pretty nifty application. This is what's called an integral pier cap. Instead of something like this where you have your beams sitting on a pier, and you have a clear transition between your superstructure and sort of the beginning of your substructure, this is what's called an integral pier cap, where you can see the girders are framing in to this beam that's actually bolted directly to this column. So you're kind of integrating, no pun intended, there's where the integral comes in, but you're integrating the pier and the girders all into this single assemblage. So just something to think about, food for thought for other instances. This is just an example of an integral pier cap. This one you can see though is also encased in concrete as well. There's another one. I would be remiss if I didn't at least mention, some concrete alternatives. Yes, we do have a fair amount of concrete alternatives for these types of structures. There are there are some different construction considerations that you need to consider, but sometimes a lot of these are the same. Concrete bridges, just like steel bridges, are subjected to that staged construction experience, and you have to consider that sequence as well. Now, you're considering it maybe a little differently, but you're still having to consider it. You're still having to go through and recognize, okay, maybe I'm setting my beams and then I'm casting a deck on top of those beams. So I've got this staged element of construction. Just like with concrete, there are some traits that are, or just like with steel, there are some traits that are unique. We can still do things like a haunch girder, increasing the depth of that girder where we're going to need it, where we're going to need those maximum forces and what have you. We can also do similar things with concrete as well. We can curve it, use that similar box shape, get that torsional behavior that we like. We can also do that from a segmental fashion, taking each segments and sort of, jacking them together in a post-tension fashion, which if you've had a course in pre-stress, you've probably heard, and talked about the difference between pre-tension and post-tension. You all have heard that. Or how many have had pre-stress? Did y'all talk about stuff like that? Okay, all right. This is just talking about some different construction techniques. This particular bridge was constructed using a launched bridge technique, which essentially the way a launched bridge works is you've got support A and support B, and obviously you need a bridge in between them. And the idea is you literally start at support A, build the bridge this way, and launch it forward. If you've got some really deep chasm to cross and what have you, this might be a pretty advantageous solution. So it's always a pretty nifty construction process, at least I think it is. Again, like steel, you can have very similar structures. Again, that rigid frame concept as well in concrete. Also, if you've had pre-stress, I'm sure you've seen these before, your AASHTO type 3s and what have you, bridge girders and whatnot. Obviously a pretty straightforward pre-stress element and a pretty popular one. Again, though, if you've had pre-stress, you can probably understand why I don't cover this, because you cover these till you're blue in the face when you take pre-stress. There's no really point to talk about it in here. This is just them setting pre-stress elements for a given bridge. Little more rare, but might as well mention it. There's, the bridge industry is heavily dominated by steel and concrete, but there are other alternatives. There's nothing to say you couldn't go with a timber solution. I mean, there is a section in the AASHTO spec solely for timber bridges. So, I mean, they're there, but obviously they are not as common as steel and concrete. Just some other options. We've got fixed arch structures, and just looking at different arches. We have a tied arch, which is essentially looking at connecting the bottom ends of these this arch and creating a little bit of tension in the system. We have two hinged arches hinging the bottom support on each end. I have a feeling at least some of you have seen this bridge before. Never. Arguably the most famous bridge in our state. Go find a commemorative quarter and you'll see that on the back of it. If you ever have a chance to go on the bridge walk and you haven't, it's worth it, I think. It's worth it the first time, right? Not the fifth time. One thing I haven't really mentioned is trusses. And obviously trusses are a very clear option for bridges. But one of the things I find interesting about it when you look at trusses is trusses look more like beams with holes in it when you really think about it. For instance, if I look at this bridge, I can tell you that this bridge is basically a series of simply supported trusses stacked on piers. And the way I can tell you that is look at these trusses. Isn't it funny how these trusses kind of look like moment diagrams stacked over and over again? That's because they are. I mean, again, a truss is really just a beam with holes in it. And what they're doing is they're trying to arrange that truss to support those loads. And those loads are moments. So, you know, you look at this and you say it's really acting more like a beam than you would think. Again, I mean, we have sort of a more triangular structure here, but you think about it, the concept's, you know, very, very similar. Now, in terms of arrangements, a through truss is where, you know, you're sort of, no pun intended, you're driving through the truss. Deck trusses are where the truss is under you. The driver wouldn't even know what was going on under the structure. But again, same concept, increasing the depth right there at the piers because that's where the maximum moments are. Same thing here, long span through truss, same story. These are some other fancier and different types of truss systems. I'm going to skip through some of this pretty quickly. I mention these bridges just because they're cool. I'm going to be frank, we're not even going to come close to talking about these types of bridges in this course. And the reason why is you can be a bridge engineer your entire career and never touch a bridge like this. Bridges like this and the New River Gorge and the Golden Gate Bridge and whatnot, they are the rarities. I mean, when you're a bridge engineer, you know, or when you're interested in bridges, or you go talk to the general populace about bridges, the first thing they think about is Golden Gate Bridge and Brooklyn Bridge and these massive, unique structures. But that's the whole point. They're unique. There's only, so many of them in the country. There's about 600,000 bridges in the United States, and the average bridge length is about 50 feet. Okay, so what the taxpayer spends their money on, and what's going to keep you busy as a bridge engineer, are your 60-foot creek crossings and your, county road bridges, the stuff that's, that's built day in and day out. And that's the stuff that we're going to focus on really in this class. We do complicate it a little bit just to make sure that you're learning, a little bit more, but arguably that's going to be our main focus. But don't get me wrong, I still think these things are cool, so I'm going to take a few minutes and show them to you. But yeah, cable-stayed bridges are going to be used when your span lengths are starting to get pretty significant. You can see a couple examples of that. This is just during the erection of one. Suspension bridges are for your really, really, really long bridges. Longest bridge on the planet is a suspension bridge. So that's for when you've got crazy significant span demands that you've got to meet, crossing bays and what have you. I just throw this in because I thought it was nifty. Historically, suspension bridges didn't have cables. They were just I-bars over and over and over again, lapped over. I actually took these two pictures, and I wish I had better ones in the PowerPoint, but I took these pictures when I was in Budapest, and it's a similar story. These aren't actually cables as much as they are I-bars lapped over and over. And I don't know, but I thought this was kind of interesting as well, that support condition. It's literally, a cylindrical support stacked on top of a cylindrical support, and that's what's been holding the bridge up this whole time. And I just thought that was really interesting, that had stayed there and it was stable this whole time. But that's just me. Obviously Golden Gate, I don't think there's really much to say about that. And these are just the really quirky ones, the really nifty ones where you've got river traffic or bay traffic that you've got to withstand. Things like lift bridges where you've got a segment of the bridge that lifts out in order to permit boat traffic. A bascule bridge where both ends lift up. Swing bridge where the bridge actually swings through. Don't get me wrong, the mechanisms that run these types of bridges get kind of nifty, and don't get me wrong, the applications are a little wild, but it's still a bunch of beams and columns and connections. It's still steel and concrete, so it's still going to behave the same way. That should be at least a somewhat familiar example, Tower Bridge. A little bit closer to home and a little more classical, some covered bridges and whatnot. We're not going to be designing those, but just thought they were worth mentioning and thought worth looking over. So it's kind of interesting to see how we go from, these old covered bridges to the modern interchanges that we do today. And there wasn't a terrible amount of time, historically between this and this. So I just think that's kind of interesting. So not to disappoint you, but we're not going to do these bridges, okay? And we're not going to do them because they're just not done that often. It's just the facts. What's done most often are things like this, regular steel I-girder bridge, regular simple span bridges and what have you. That's what's going to keep bridge engineers busy and occupied for years to come, and that's what I focus on in this course. Just a little bit of data. If you've ever heard of some of these topics, and you might not have, so I'll cover some of this. The National Bridge Inventory is basically this mega huge database of just about every bridge that can be compiled in the United States. Now, I did a little bit of analysis on the 2013 database. I doubt that this data has changed drastically in the last 3 years, but it is what it is. There's a little over 600,000 bridges in the NBI representing bridges in the United States. You look at the average span length of those bridges, it's only 48 feet, okay? Most bridges aren't that, okay? So that's why I don't cover it. I spend time covering stuff you're actually going to see in your jobs and in your careers. So that's the type of stuff that we focus on. And like I said, we're mainly going to focus on steel bridges. The first part is going to be the basis of design, loads, and things like that. And a lot of that's going to be, pretty neutral. It doesn't matter what type of bridge it is. That stuff's going to be applicable. But I focus on steel in here just because you have a full course devoted to concrete, and I don't see the reason in doubling up. All right. Oh, does anybody have any questions just at all about anything in general? Anything at all? Okay. I do want to start getting into this material a little bit, and I've done this a number of times, gone through this class a number of times, and it's kind of difficult to just jump right into it and say, okay, here's bridges, because there's always two sides of the equation in the world of structural engineering. There's the loads and there's the resistance. And let's say I started talking about the loads, and I started talking about the different types of dead loads and live loads and da-da-da-da. When we actually start computing them, we got to say, all right, let's compute all these loads. Oh, wait, now we got to go back and start computing things like moments of inertia and section properties and areas and whatnot. And we end up backtracking, and you take one step forward, then you've got to take 2 steps back and go back and cover all of this stuff that you wish, you look back and go, I wish I had just taken some time and just gone through, some of this pedigree, fundamental information at the beginning. So one of the first things that we're going to do is look at section properties. And by doing this now, what it will do is it'll help us sort of speak the same language down the line when we start talking about the dead loads on bridges, the live loads on bridges, how strong bridges are, computing things like plastic moments and yield moments and depths of webs and compression and all of that stuff. We'll be able to speak the same language because we've gone through some of this fundamental information already. So I want to pass these notes out as well. All right, so I think that's all of them. All right, tell you what, this is what I'm going to do. Start at the back. Let's see, 5. There's that. There's that. And I think that's everything. Okay. Actually, I'll just go this way. I'll be lazy. All right. Now this part I'm going to take a little bit of time and sort of dig deep into this set of notes, because we're actually starting to get into the nuts and bolts of what it is we're going to do this semester. So I'm going to take my time with this. All right. So I start off with section properties because these are some fundamental calculations that are going to affect everything that we do from here on out. When we do stress calculations, you all remember from strength of materials, right? Remember that whole sigma equals my over I? Remember that? Well, we need I. We need the moment of inertia. We need those properties. That stuff's going to be pretty important. We need those values to do those stress calculations. If you've ever run any piece of structural analysis software, you have to put in I. You have to put in a modulus of elasticity. You need those properties to run the program. When we start doing resistance checks and capacity checks to see if a given element is safe to resist those loads, we're going to need these properties as well. So these are just so fundamental, we might as well get them out of the way and do it first. Okay? Now, I say section properties. I want to make sure everybody knows what I'm talking about when I say section properties. I'm talking about if I take this, bridge beam or what have you, and I use the secret weapon of structural engineering, which is a samurai sword or a lightsaber if you happen to be a sci-fi fan, and I cut a section right through that bridge, and I'm looking at this beam, looking at the deck, I'm talking about the properties associated with this section. Things like its area, its centroids, its moments of inertia, section moduli, all of that stuff. That's the type of stuff that I'm talking about when I say section properties. Everybody okay with that? Okay. All right. Now, I'm not going to talk about the loads in this discussion very heavily. However, I do need to discuss them a little bit so that you can kind of understand the motivation for what we're going to talk about. All right? So in bridges and in structural engineering in general, you've probably heard the term dead load and live load. I don't like to use dead and live in this course because there's so many different types of dead loads and so many types of live loads. I like to call them permanent and transient. So permanent loads are loads on the structure that are always going to be there. Things like the self-weight of the beam, the concrete slabs, the barriers, if there are lights on the bridge or any utilities on the bridge, the asphalt, if there's asphalt or any bituminous overlay or anything like that. All the permanent loads on the structure, that's a category in and of itself. The other category are the transient loads, the vehicular traffic, dynamic impact, if we're going to consider any seismic effects or anything like that. Stuff that's not always on the bridge, stuff that moves. Okay? What makes bridges unique, and specifically the case when you're dealing with a composite structure, something like this, is that concept of staged construction. So I want you to sort of mentally picture what's going on during a bridge construction, during a typical bridge construction. So let's say I'm trying to cross a bridge from here to here. Okay, so I've done all my earthwork, done all my grade work and what have you, and I've driven piles or whatever, and capped my abutments, and I'm ready to place my girders. So what happens? Excuse me. First thing I do is I take the beams, I set them down, right? Okay, so what loads are the beams subjected to right then? What loads are they subjected to? What's that? They have to support their own self-weight, right? Obviously, all beams have to support their own self-weight. Well, what is resisting that load is the steel beam by itself, just the steel beam, okay? Then I start connecting everything, putting all the cross frames or diaphragms or what have you in, and erecting the rest of the superstructure. Then it's time to start getting ready to put the deck in. So, setting in all our form work and what have you, starting to tie up our rebar and what have you, getting ready to pour the concrete. Then I pour the concrete. Again, all those loads have to be supported by the steel beam by itself. Make sense? Okay. Now, what happens? Concrete cures. It gets hard, right? Concrete cures. All right. For a composite steel bridge, we tend to locate a fair number of shear connectors on the top flange so that that deck and that girder are locked together. That's what it means for it to be composite, that they're bending and behaving together. When I drive a truck over that bridge, it is not just the steel beam by itself resisting the load of that truck. No, it's the steel beam and the concrete acting together. You see what I mean? So we have different sections that are going to matter. When we're looking at the weight of the wet concrete and the self-weight of the beam, we have to consider just the steel shape by itself. But when we're looking at the vehicular loads, the truck traffic and what have you, we have to look at that composite section, the steel plus the concrete. So we have to look at different sections and look at the different properties associated with those sections. So it's a little bit of a loaded topic worth discussing. All right, make sense? Everybody kind of understand where we're at and where we're going? Okay. All right. Now, before we start just taking a nosedive and starting to calculate this stuff right now, I want to take a little bit of time and go into some terminology, some discussion of different parameters that are going to affect what we're going to talk about, things like effective flange width, material properties, the rebar. We're going to take each of these one at a time, and we're going to break them down. I want to make sure everybody knows what we're talking about and why we're talking about it. Okay? So let's start off with the terminology. Okay? And I'm going to take a little bit of time, make sure we're digesting what's going on this slide. So I prepared this just to kind of illustrate some general quantities and some general terms that I'm going to throw out and use throughout the semester so that we're all speaking the same language and we understand what's going on. Start off, let's talk about the beam, the actual steel beam. So we're looking at an I shape. So I'm saying that this I shape consists of a top flange, a web, and a bottom flange. Now, if you're dealing with a rolled shape, like a rolled I-beam, then your top flange and your bottom flange are going to be the same. But on larger span bands, you're not going to use a rolled I shape from the mill. You're actually going to craft a plate girder with a different size top flange than you have the bottom flange. You're going to be able to tailor those flange sizes to meet your given load demand. So you're going to have different, it's very potential, there's a high potential that you could have a different top flange than you would a bottom flange. So I wanted to introduce that notation and make sure everybody's on the same playing field. So if I've got here top flange B times T, I'm saying it's B wide and it's T thick. So this is the width of the top flange, thickness of the top flange. Okay? Sound good? Now, I'm using this notation very carefully because later on when we actually start opening the AASHTO spec and we start actually looking at the equations that are in the specification, I'm doing my best to ensure that this notation matches what's in the spec so that, if I use a capital D to represent the depth of this web, it's capital D in the spec too. So I'm trying to be consistent with that as well. Now the web, I'm going to say it's D deep, and I'm going to say it's T wide, or the thickness of the web. And then with the bottom flange, same deal. So far so good? Okay. Now, what's going on with the deck is going to take a little bit of discussion because I've got this effective flange width, integral wearing surface, total slab thickness, structural slab thickness. We're going to take a little bit of time with that. Okay? So bear with me. All right, so I'm going to zoom into that a little bit and make sure that we're attacking this, each of these topics one by one. Before I continue, everybody okay with everything so far? Okay, all right. So let's tackle each of these one at a time. Let's start off with this, the haunch. The haunch is what we define, basically what we're trying to do with the haunch is we're trying to represent the fact that there is, in actuality, a little bit of a gap between the girder and the deck, and you're thinking to yourself, wait, is the deck floating in space? No, it's not. What's going on is if you look at typical forming methods for how we form decks, you look at a lot of these SIP forms, they tend to have these flutes to sort of receive the wet concrete. And because of that, if we sort of strike a line, we'll find that the beginning of that flat portion of the bottom of the slab is actually a little bit higher up from the beam. There's actually a little bit of a gap. So in order to be conservative, we tend to neglect all that concrete below the flutes. Okay? Does that make sense? So there is a gap usually. Now, in terms of specifics, so that we're all speaking the same language, what I'm defining as the haunch, I define it as the distance from the top of the web to the bottom of the slab. Okay? So, for instance, if this flange is, I don't know, 3/4 of an inch thick, and this haunch is 2 inches, that would make this little gap, what, 1.25 inches? Everybody with me on that? So I just want to make sure we're all speaking the same language. Okay? Now, does everybody understand what's going on with the forms and why it tends to be raised up a little bit? Okay. One thing to keep in mind is something I've been pretty fast and loose on. We will actually spend a fair amount of time this semester looking at just the studs themselves and actually figuring out how many studs need to go on the beams and in what spacing. The only point I'll make is if you look at a steel beam in a building as opposed to a steel beam in a bridge, there is an ocean of studs on bridge beams, okay? And the reason can be summed up in one simple word: fatigue, okay? Unlike buildings, and don't get me wrong, buildings see these types of forces as well, but in no way, shape, or form at the same magnitude. Bridges see a lot of cyclic loading. They're loaded, unloaded, loaded, unloaded. Trucks drive over and over and over again. And because of that, what can happen is elements like shear studs and connections and what have you, and those fabrication details, they can experience failure at really, really low stresses. To give you somewhat of an analogy, have you ever taken a paper clip and bent it back and forth a few times and then it kind of just gets softer in your hand and it kind of snaps? You know what I'm talking about? That's what's called low cycle fatigue, because you do it, only a few times and the paper clip fails. What we're doing is we're not applying those very high stresses, but we're doing it millions of times. So we get, what can happen is you can get failure limits that are a lot lower than you would think. Steel tends to have a yield stress, or at least a pretty common grade for what we use in bridge applications, of 50 KSI, so 50,000 pounds per square inch. But we can have fatigue categories that can fail at 6 KSI or 8 KSI or what have you. So just worth mentioning. Okay. Just real quick, typical dimensions for the haunch. I sort of went off, but bear with me. This is bridge engineering. I'm going to go off topic quite a bit. Typical values for haunches are anywhere from 2 to 4 inches. A really common value is 2 inches. We're going to use that for an example here in a little bit. All right. So that explains the haunch. I want to talk a little bit now about this concept of an integral wearing surface, because if you notice, I've got two slab thicknesses. I've got a total slab thickness and a structural slab thickness. The difference is that the structural slab thickness is a tad thinner, and it's a tad thinner by this integral wearing surface. The reason for including this is over time we tend to assume that a small little layer of that concrete deck is going to go away, okay? And there's a number of reasons. Just general wear and tear, that's a big reason. The truck scraping the snow and the ice off the bridge, that tends to wear the concrete out over time. So what'll happen is we'll want to make how's the best way I want to put this? We'll want to make a delineation between how much concrete we're actually considering for capacity and how much concrete was there when it was cast. So to give you an example, we might cast, like when we're out there in the field and we're pouring the bridge deck, we might pour 8.5 inches thick concrete deck. We might pour 8.5 inches. But over time, we're going to assume 1/2 inch of that's going to go away due to it getting scraped off, due to wear and tear, and what have you. The point is, when we calculate loads, the loads that are on that structure, we're going to want to use the total thickness, okay, the full 8.5 inches. But when we're on the other side of the equation calculating the resistance, how strong that given element is, we can't count on that full 8.5 inches because we're assuming some of that's worn away. So we're only going to consider the structural thickness. We're only going to consider the 8 inches. Does that make sense? All right, and each state tends to use different values. One thing I haven't really mentioned this, and we'll talk about this more probably next week when we start digging a little deeper into the specification. But in America, we have a national AASHTO LRFD specification, which is the specification we're going to cover in this course. And the way that works is AASHTO is sort of the minimum standard, okay? But each state can come in and say, well, I have increased standards. And here's a common example, or a simple example to go off of. So AASHTO has a standard vehicular model, a series of loads that they use to represent truck traffic in the United States, typical truck traffic. And that's the model that is the minimum standard across the country. But you go to Kentucky, and Kentucky says, that's great, we're going to use a model that's 25% larger, okay? And that's because in Kentucky they see larger loads, and that's what they need to use. So that specification makes sense for Kentucky. And every state sort of has their own flavor and own preferred construction practices and preferred specs, and it is what it is. It's one of the things that you have to negotiate when you're a bridge engineer. So one state, though, where the regulations are very interesting is Pennsylvania, because they sort of have their own complete way of doing things. There's a common saying among bridge engineers that when you're designing bridges, there's Pennsylvania and then there's 49 other states. So but that's another story for another day. Okay, so far so good? All right, so let me go back to this. So I wanted to talk about the slab thickness, so how we've got these different definitions between a total slab thickness and a structural slab thickness. I wanted to define what's going on with this haunch. Next thing I want to do is I want to talk about this concept here, this effective flange width. What do I mean by that? Okay, so what I want to do is I want to look at a generic cross-section for a bridge. And I just wanted to use this for the purposes of discussion. So keep it simple. We got two 12-foot lanes, two 5-foot shoulders. That's a pretty typical highway bridge in the United States. Yeah, that's pretty typical. All right. So I've got this cross-section here. There's nothing magic about it. This is just set up for the purposes of discussion. Okay. Now, what I want to do when I'm evaluating a given beam, let's say this beam or maybe this beam, is if I'm looking at the composite beam, it's the steel plus a portion of the deck. The key word is a portion. For this beam, let's say if I'm looking at this second beam over, the question I'm trying to answer is how much of that beam is applicable for, or how much of that deck is applicable for this given beam? Is it this much? Is it this much? Is it this much? How much of that deck can I consider effective for that beam? Okay? And if you, I have a 4 there for some reason. That's going to bug me. Oh, enable editing. Sorry, I don't know what happened there. I was playing around with this right before class, so of course I had a typo in it. Now, mechanically, what happens is, if you look at the stresses in the deck, they tend to decrease away from the beam. So what we try and do is we try and cut out a representative slice of that deck and say, okay, that's the portion of the deck that's effective for that beam. If you've had reinforced concrete design, you've done something pretty familiar or pretty similar when you look at T-beams. You've got a floor system that has a slab and a series of rectangular beams, and when you look at that in a composite state, you cut out a slice of that slab and you've got a T-beam, right? I'm sure you all have done something similar when you took concrete design. And when if you look at the American building spec for effective flange width, there's all these weird little rules, like it's the minimum of the span length over 4, or all these different categories. We kept it pretty simple in the bridge industry. So I have here a small little snippet from the spec, and I'm going to read through some of it, but I'm just going to read this out. So, unless specified otherwise in a series of articles, which we can talk about later, The effective flange width of a concrete deck slab in composite or monolithic construction may be taken as the tributary width. Okay? So if you remember from structural engineering, if you've got a series of loads on a given floor system and you want to determine how much load goes to a given beam, you just use the tributary width, which for a given beam is halfway between adjacent girders. That tributary width and that effective flange width are the same thing in the bridge spec. There was a series of studies done, I want to say it was like 2006, 2007, where they were trying to just ask the question, can't we just use this and just keep it simple? And the answer was, yeah, close enough for government work. So the tributary width and the effective flange width are the same thing in terms of the bridge spec. One thing, though, is that can create a little bit of a complication when you're analyzing the bridge, because if I look at the interior beams versus looking at the exterior beams, they've got different effective flange widths. Like, if I look at this one, it's what? Like, what, 10'6"? But this one over here is what? That plus half that. That's not 10'6", right? Make sense? So because of that, I can have different section properties for interior girders and exterior girders. Make sense? So one thing about this course and about bridge engineering in general is make sure you're cognizant of your bookkeeping, okay? Making sure you're well organized with what you do. All right. Sound good? Okay. All right. Now I'm going to bring it back a little bit and go back to strength of materials. I don't know how long it's been since you took strength of materials or mechanics of materials or mechanics of deformable bodies. There's like 8 or 9 different names for the class, but it's all the same thing. This goes back to that whole sigma equals my over I. Everybody's heard that before, right? You know what I'm talking about there, right? Well, sigma equals my over I, if you recall, assumes that you've got a beam made of a single material, that beam is made only of steel, or it's made only of aluminum, or only of copper, or whatever. Well, we got a problem here because we got a beam that's made out of steel and concrete. How do we handle that? Well, we take one of those materials, in this case we take the concrete, and we transform it into an effective lump of steel. Okay? If you've taken reinforced concrete design, you do something similar when you calculate deflections, but it's actually the opposite. You take the rebar in the bottom of the beam and you transform it into an effective lump of concrete. Here what we're doing is taking the concrete and transforming it into an effective lump of steel. So what ends up happening is if you've got this effective flange width, because steel is so much stronger than concrete, this concrete is then represented by this smaller lump of steel. So we transform it by dividing it by N. N is the modular ratio. So I'm sure you all have seen stuff like this before in concrete design, am I right? Okay, all right. So E is the modulus of elasticity of steel, E sub S. E sub C is the modulus of elasticity of concrete. All right. Steel, folks have had me for steel. What is the modulus of elasticity for steel? It's the one number I said you are not going to forget. So there we go, 29,000 KSI. There we go. What did you say? Big money, no whammy, no whammy, no whammy. Stop. Wah, wah. References from the 80s. Gotta love them. All right, all right, real quick. So modulus of elasticity of steel, modulus of elasticity of concrete. When we calculate N, we typically round it to the nearest whole number. Don't worry, if you feel like I'm throwing out like a massive amount of details at you, we're going to practice some of these with a quick example here in a little bit. So don't worry, we'll exercise these pretty quickly. But typically we round N to the nearest whole number. We don't use an N of 7.962. We just say 8. Just keep it simple. Now, for steel, the modulus of elasticity of steel is 29,000 KSI. For concrete, we have to compute it, but if you're dealing with normal weight concrete, there's a pretty easy shortcut. We just take 1820 times the square root of SC prime in KSI, and that'll give us a shortcut answer really quickly. All right. So far, so good? Okay. All right. So since we've gone through and talked a little bit about the terminology, let's actually start breaking down the sections that we need to compute. Now, I'm going to take my time with this to make sure that this makes sense, because when we talk about the loads, we will really dig this in significant detail. But I wanted to at least cover a little bit of it so what we say makes sense. When we consider our load sequence, and I'm just going to leave it at this for now and discuss it in more detail later, but when we consider our load sequence, we have to consider three types of loads. We consider permanent loads and transient loads, but I'm splitting up the permanent loads a little bit. I'm saying permanent loads that are applied before the section achieves composite action or before that deck cures, and then permanent loads after the deck cures. So what do I mean by after the deck cures? I mean things maybe like concrete jersey barriers or overlays or future wearing surfaces or things like that. There are loads that are applied after the deck is cured, but there's obviously a significant number of loads that are applied before the deck cures. So I'm splitting that up into three categories, and also the transient loads. Now, the permanent loads that are applied before the concrete cures, before we get composite action, they have to be resisted by the steel beam by itself. So that's section number one, the non-composite steel section, just the steel section by itself. Okay? The transient loads have to be resisted by the composite section, the steel and the girder acting, or the steel and the concrete acting together. When I drive a truck on the bridge, the deck and the girder are acting together to resist that load. Okay? Now for terminology, I'm going to call this the short-term composite section, because those loads are only on the bridge for a very short period of time. Truck drives on and it's off, and then it's gone. Okay? Now, to determine the short-term section, I take that effective flange width and I divide it by n, that modular ratio. Sound good? Okay. Now, here's where I want to take a little bit of time. Remember that I was talking about those permanent loads that are applied after the deck cures, things like the barrier, bituminous overlay, future wearing surface, utilities, things like that. They're on the bridge all the time. Okay? They're not going anywhere. Okay? Now, if you've had pre-stressed concrete, you know as well as I do that concrete is a material that's properties change over time. Concrete undergoes things like creep and shrinkage and what have you. And if you've had pre-stress, you've heard this stuff before. Well, because of that, concrete's properties not only change over time, but they get a little bit weaker. Okay? So when we look at these loads, these permanent loads that are applied after the deck is cured, because they're there all the time and they never go away, they're applied on the long-term composite section. Okay? In the long-term composite section, we take that effective flange width, we don't divide it by n, we divide it by 3n. So we're dealing with a smaller deck. And we do that because over time, you know, we have creep in the concrete and those effects that can tend to weaken it. Okay? So if we're looking at sections in positive bending, we have three section properties we have to assess. The steel beam all by itself, the steel beam plus the composite deck, you know, short term and then long term. Make sense? And then keep in mind, these two can be different if you're looking at interior girders versus exterior girders, because that dimension can be different. Everybody good? Now, that's positive bending region, where smiley face, where the concrete is in compression. When the concrete is in tension, we have another one we have to consider. We can't always use just the steel plus the concrete, because in negative bending, like a region that you would see right here, this region over the pier, the concrete is bending like, or the beam and the bridge is bending like this. So the concrete is in tension. Make sense? So what we've got to do is look at a fourth section, which consists of the steel and the rebar. steel and the reinforcement inside that section. Now, we can do this two ways. We can break out the bridge plans, start cutting up the flange width, and literally count every single bar, and then try and do that. No, I'm not doing that. I'm going to come up with a little bit of an easier way of determining that section, and I'm going to do it by looking in the code. Okay? So this is another little snippet from the code. Again, we will take the code in its grand glory later. I'm just identifying given snippets for the purposes of our discussions today. But when you're dealing with negative bending regions, the code specifies that you have to provide at least a minimum amount of reinforcement in those given sections. And instead of counting up every single piece of rebar, what I'm going to do is conservatively assume that I've at least got the minimum. So I'm going to use the minimum. So how's this going to work? I'm going to read the spec, and I've got these highlighted portions for purposes of elaboration. So the total cross-sectional area of the longitudinal reinforcement shall not be less than 1% of the total area of the deck. So that's that one on the left. So what that means is, if I look here at this steel plus longitudinal reinforcement, I would compute the area of this deck and say 1% of that, that's all this rebar. Okay? All this rebar, that's 1% of this area. And how do I lump it? All right? 2/3 in the top layer, 1/3 in the bottom layer. So I take all this area, 1%'s all of it, 2/3 goes up here, 1/3 goes down there. That's pretty vague though. What's this whole up there and down there? Well, I place this rebar according to cover requirements. Y'all remember that? You have to have a certain amount of embedment and for corrosion issues and what have you. I go to the spec and I say, all right, let's look at cover requirements for reinforced concrete. Now for the top, since if we're talking about an area like West Virginia where we're going to have a lot of de-icing salts on the top of the bridge deck, we got to have at least 2.5 inches of cover, okay? So this top layer, that larger top layer, 2.5 inches below the top. That's the cover requirement, okay? And that'll give us our space, all right? For the bottom, up to number 11 bar, we go 1 inch up. So 2.5 inches down, 1 inch up. Sound good? We'll just assume it's all effectively lumped right there. All right, and then for the purposes of our calculation, when we're trying to do spacing, we can just assume that they're number 6 bars, which, let's see if y'all remember. What's the diameter of a number 6? Let's see if we remember. So who said that? There, 3/4, right? Number 6 is 6/8 or 3/4. Whoever said that. All right. Sound good? Okay. So when we're looking at negative bending regions, we have some additional sections to consider. Again, this is just the stuff we want to get out of the way now so that when we start really talking about the loads, really getting into that stuff, we'll be able to speak the same language. All right. Sound good? Any questions? Okay. All right. What time is it? You tell me. I'll sort of let you all run the show, but you know, we're going to be in here for 2-some hours every week. Do you all want to take a 5-minute break in between and then meet back later? Y'all want to do that? All right. Let's go ahead and take a 5-minute break, 5 or 10-minute break, and then we will come back and we will do an example and we'll go through some calculations. Sound good? All right. I can't think.